Okay, let's find the equations for the following network. So this network consists of three pipes and three junctions A, B, and C. So the first thing that we need to do is to assign some direction of the pipe to the pipes, to the flow in the pipes. So if the flow is coming in this way and going out on those 2 points, so probably the flow is going to be something like that. And in pipe 1 uh, it could be either way, so we can assume that this is the direction in pipe 1. Now we also need to define the direction of the loop. It's a good idea to keep a simple direction, so the same direction for all the loops. In this case we just have one loop. The third thing that we need to do is to corroborate that there is conservation of mass in the whole system. So we have one input and two outputs. So from the information in the diagram we have that QC is the input and the outflows are QB and QA. So QC is 1 and QB is 0.3 and QA is 0.7. So this is in agreement with the conservation of mass, 1 equal to 1. Now let's start by writing the equations of the joints. So let me go to the second page. I already have here the direction that we mentioned before, and let's start to look into the equations for the junctions. So the first one is A. For A we have two inflows and one outflow. So remember that we are assuming inflows are negatives and outflows are positives. So the equation for junction A is QA minus Q3 minus Q1, and that should be equal to 0. Now for B we have QB is outflow, the Q in pipe 2 is in, and the Q in pipe 1 is out. So QB, which is out, equal to minus Q2, which is coming in, minus Q1, which is coming out. And finally, for junction 3 we have that QC is coming in and out is Q2 and Q3. Q2 and Q3 out. Now the loop equation. So we are going to start with this section. So the direction of the flow in the pipe that we assume is opposite to the direction of the loop, so the sign is negative, and so the pipe constant is K1 multiplied by the flow rate in the pipe 1 square. In the second section we have again that the direction of the loop is opposite to the direction of the flow that we assume, so is negative K2 multiplied by Q2 squared. And finally in the third pipe we have Q3, which is in the same direction of the loop, so it's positive, and the pipe constant K3 multiplied by Q3 squared, and again it should be equal to 0. So we have all the equations, one for each junction and one for the loop. In this second example we have a network that consists of two loops. In this network we have 1, 2, 3, 4, 5, 6 joints. We have 7 pipes, 1, 2, 3, 4, 5, 6, 7 pipes, and we have two loops, as I mentioned before. So 7 pipes means that we have 7 flow rates, which are the unknowns. So we have Q1 to Q7 unknowns. Now, the first thing that we need to do is verify that the conservation of mass is achieved. So the inlet is 0.125 cubic meters per second, and the outlets are 0.012, 0.063, 0.025, and 0.025. So they should add 0.125. So let's see. So we have 0.012 plus 0.063 plus 0.025 plus 0.025. So in total we have 5, 10, and 5, 15. So 5 and carry 1, and then we have 2, 4, 10, 1, and another one is 12. So 0.0125. So which corresponds to the inflow. So conservation of mass is achieved. So now let's have a look to the equation. So I number the equation here from 1 to 7. We can have 8 equations because we have 6 joints and 2 loops. So there is one equation in excess. So I decide that the equation for node B is not necessary. So this is the order of equation. F1 corresponds to joint A, F2 corresponds to joint C, F3 to D, F4 to E, F5 to G, to F, and F6 to loop 1, and F7 to loop 2. Let's verify some of the equations. For node A, we have 0.125 inlet, and we have 2 outlets, 4 and 1. So assuming that the inlets are negative, we have 0.125, and the outlets are Q1 and Q4. So that, by the way, should be equal to 0. Equation for C, for example, is this one. So we have an outlet of 0.012, so outlet positive, also outlet of 6 positive, and an inlet of 5. It's another one, just verify this one. So this is the equation for E. So for E, we have outlet is 7 and in is 2 and 3. So 2 and 3 are inlets, and 7 is outlet, and also outlet is 0.025. So all these equations are equal to 0, every single one. Let's take loop 1. So for loop 1, remember we are assuming this in the clockwise direction, and for pipe 1 is in the same direction of the loop, so it's positive. 2 is in the same direction, so it's positive. 3 is in the opposite direction, so it's negative, and 4 is in the opposite direction, so it's negative. So and each of the terms are the pipe constant multiplied by the flow rate in the pipe square. So the same thing can be achieved in 7. And the seventh equation, which is equation for loop 2. So 5 is in the same direction of 2. 6 is in the same direction of the loop. 7 is in the opposite direction of the loop. And 2 is in the opposite direction of the loop. So these are two negatives.